Okay, this is the video for 3.9 derivatives of log and exponential functions. This will be our last set of special derivative rules that you need to know, that you need to memorize. One of these rules today is pretty easy, um, but also pretty unique. We're going to start by looking at e to the x, y equals e to the x. I'm going to claim it has a special derivative. Can kind of already see the answers over on the right. Um, to derive this derivative rule, we are going to need to know a little something about the function e to the x minus 1 over x, which I have a graph of here. Immediately replacing x with h, I could call the variable really whatever I want. The reason I'm using h here is because this function is actually going to be related to derivatives of e to the x, which we're going to explore through the limit definition, which is where h is involved. So imagine a graph with h on the horizontal axis, e to the h minus 1 over h on the vertical. I pulled this from Desmos. You can check it on your own. What's notable here is that while this function is undefined at 0, the limit as you approach 0 from either side is 1, which is what we're going to pull from this in a moment. Anyhow, going back to y equals e to the x, I'm interested in the derivative of this function. It's an exponential function, which you should be familiar with the shape of it from algebra. It's a function that gets bigger, bigger, bigger as x increases, and it gets bigger faster as x increases. So we already know it's going to have a slope that's always positive and always increasing. Let's see what it looks like in the limit definition. I'm going to start by saying y prime or dy dx would have been my preferred notation. Is a limit as h goes to 0 of my e to the x function with x plus h plugged in minus e to the x all over h. This is just a version of f of x plus h minus f of x all over h. You can go back to your notes from last chapter to review the limit definition if you like. But I've set it up here. I want to figure out what exactly it's telling us. I'm noticing that both terms in the numerator involve e to the x. In fact, using pre-algebra rules, I can rewrite e to the x plus h as e to the x times e to the h. And then I truly can factor e to the x out of both of those terms. And because our limit involves the quantity h, I can pull anything without an h completely to the outside. So once I factor out this e to the x, I can move it even to the left of the limit itself. And now I have a limit as h goes to 0 of e to the h minus 1 over h. What does this limit do? Well, that's why we have the graph here. The whole purpose of the graph is to show us evidence that this remaining limit just turns into a 1. And so I replace it with a 1. And all of a sudden, I see this perhaps surprising result that the derivative of e to the x is itself. Here we have a function whose slope at any particular x value is the same as the y value at any particular x value, which is quite curious, but also very easy to remember. So officially, we have the rule over here on the right panel. Derivative of e to the x is e to the x. The follow-up question would be, okay, e is a fairly special base as far as exponential functions go. What about derivatives of exponential functions with other bases? So here I have derivative of a to the x. And similarly to e to the x, the derivative includes what we started with, but it also has a multiplier of natural log of the original base a. And I'm going to try to convince you that really e to the x had the same phenomenon as well. It's just if we were to multiply e to the x by natural log of the base e, we all know Natural log of e simplifies to 1, so I don't really see it. I can instead report the derivative as just e to the x. But really the overarching rule is derivative of a to the x equals a to the x times natural log of your base a. So these are the rules that we want to remember. And below that, we see 4 examples. And of course, we're going to get a little complicated right away. These new rules themselves are kind of easy, but they often go in conjunction with chain rules or product rules or other rules. So that's what we're seeing here. For part A, as soon as I see e to some power involving a variable x, I can instantly use that same expression in my answer, e to the x plus x squared, but it becomes chain rule. I'm thinking of this x plus x squared as being plugged into another function. It's taking the place of where we typically would have expected just an x. So I multiply by the derivative of x plus x squared. Part B is a simpler example. This is just evidence of the a to the x rule. Here we see a as 2, so y equals 2 to the x. Derivative is 2 to the x times natural log of 2. Not too much to say there. Um, okay, moving down to part C. I have a 2/3 in front, which I can just kind of bring down as a multiplied constant. E to the negative 3x to the fourth is going to come down as well, multiplied by the derivative of negative 3x to the fourth, thanks to chain rule. And then, of course, at this point, I can combine some of these multiplied constants to simplify a little bit there. All right, part D. Excuse me. 3 to the cotangent x taking the place of x. We still treat it as 3 to a variable power, so we're still interested in using the a to the x derivative, which as you can see I've done, which of course also includes a multiplier of natural log of the original base, but then chain rule. What was the derivative of cotangent? Well, here it is, and there's my answer. So be prepared to see these new rules mixed in with older rules. I'm going to go now to the next, I believe, final page of 3B notes. And on this page, we're going to use the e to the x derivative to get after another collection of rules, derivatives of log functions. We already know there is a relationship between logs and exponentials. Those are inverse functions of each other. Specifically, y equals log of x, natural log of x is the inverse of e to the x. So let's use our previous rules to explore this thing. I want to find a derivative of y equals natural log of x. And as my first step, I'm going to switch it to an exponential form. If y is in fact equal to natural log of x, I can say e to the y power is equal to e to the natural log of x power. And of course, I'm doing this because I get a really nice simplification on the right side, thanks to inverse functions. E to the natural log of x is just x. So now I've got e to the y equals x, and we're going to deal with this using implicit differentiation. The derivative of e to the y, I can say, is e to the y, but because we have a y instead of an x, we need to multiply that result by dy dx, just as we did with implicit differentiation problems. So here we see now the derivative of the left side. Meanwhile, the derivative of x on the right is just 1, and we're getting pretty close here. We're going to solve this to get dy dx by itself. So I see that dy dx is equal to 1 over e to the y. Now, I would prefer an answer in terms of x as opposed to y, and I can get it here by substituting from our original premise of this problem. The whole purpose was a situation where y is log of x, so I'm going to replace y once again with log of x. And now inverses to the rescue once again. E to the natural log of x, as we said earlier, is just x. So after all that, we learned that the derivative of natural log of x is just 1 over x. And we have that rule written down below. Again, the follow-up question, how would this apply to other logs besides natural log? So imagine log of any base, we'll say log base a of x, and I'm going to immediately make it a natural log problem because I know how to deal with those. I'm using a change of base formula from algebra. Log base a of x is equal to the natural log of that same x divided by the natural log of the original base a. Okay. Which I wish I would have written out here. Maybe the better way to think of this is 1 over natural log of a times natural log of x. And if we write it that way, we see 1 over log a as a constant that we can just bring down, and that's what our derivative looks like. Because I now have log x in a numerator, I have my derivative of 1 over x times 1 over natural log of a. So yeah, that's your last derivative rule of the chapter. And we need to just memorize those as soon as we can. And we'll move over to the right and look through these examples here. Feel free to pause these videos at any time as you write down some of the work for your notes. Let's get this out of the way. Find derivatives of the various functions. Each one of these, well, at least the first two involve logs. Part A, natural log sine inverse of x being a natural log. First and foremost, we know we're going to see 1 over whatever was plugged in. And then chain rule, using a rule from earlier this week, we multiply by the derivative of inverse sine. Excuse me. Sorry. So yeah, here is the result. I don't think there's any meaningful way to simplify that any further. Part B, we see a setup that could be treated with quotient rule. That would not be wrong. I tend to prefer product rule if given the choice, so I'm choosing to rewrite the original y as 3 times the quantity log base 2 of x to the third all to the negative 1. Okay. Um, and actually, I don't know that I even need product rule at this point because this reads more as one of our basic polynomial derivatives. I have constant times something with a variable raised to a constant power. So I can use our typical shortcut of, negative 1 times 3, take my original base with a variable, uh, subtract 1 from the power, so now it's negative 2. I just need to do now chain rule on this plugged in portion, and I need to do chain rule twice because instead of an x, we have a log function, and then plugged into that log function, we have x to the third instead of just an x. So that's what we're seeing here. With this log base 2, I'm going to go with 1 over the plugged in x to the third times natural log of that base 2. And then all of that gets multiplied by the 3x squared, which is the derivative of the x to the third. Excuse me again. Next couple lines of work are just attempts to clean that up a little bit, moving the multiplied constants together, doing some simplification of x, and so on and so forth. All right. Next one is a fun one. It's a weird one. Y equals 7 to the x squared, which first I have to point out, this is not an exponential function, nor is it a polynomial function. One of the key characteristics of exponential is that The base would have to be a constant and the variable is in the power. Polynomials, on the other hand, the base is the variable and the power is constant. Here I have neither of those things because I have a variable in both the base and the exponent. So this is perhaps a new function type. Um, but it is still something we can find a derivative of using rules we already know. And the trick, once again, is implicit differentiation. I ultimately don't like having a variable in both a base and an exponent. We don't have a rule for that. So I'd like to separate those things out. The only algebra trick we know to separate an exponent from its base would involve logs. So here I am taking the log of both sides. If I want a log on the right, I also need a log on the left. So I get natural log of y equaling natural log of the other side. And now I'm working on the right side using log properties. I'm able to expand my log of a product to pull the 7 away from the x to the x squared. And then at that point, I can pull the x squared in front of the log of x, again with a log property. And once I've gotten it into this form here, I am able to apply rules that we know with, excuse me, implicit differentiation. So with the left side, log of y becomes 1 over y times dy dx. On the right side, this first term is a constant, so its derivative is 0, and I can disregard it. The rest of it is product rule. 2x is the derivative of x squared times log plus x squared times the derivative of log. I wish I would have shown a little more work here. But it becomes x squared times 1 over x, which simplifies to just an x. If you write it out, you'll see what I'm talking about. At that point, I get dy dx by itself. I've multiplied y over. I am able, once again, to get an answer fully in terms of x because I already know from earlier that y is equal to 7x to the x squared, so I can bring that back in here. I also am multiplying that result by another copy of x, so I'm able to combine x to the x squared with x to the first by adding those exponents together. And that's how I landed on that answer. All right, we've got one more. Struggling to get through this. Sorry about that. Okay, here we go. Evaluate the limit. When we get to the AP exam next year and you see limit questions show up, um, I can almost guarantee you every limit that they give you is either going to be L'Hopital's rule, which we haven't learned yet, don't worry about it, or it's going to be something involving a limit definition of derivative. And that is what we're seeing here. At first glance, it looks kind of funky, but we realize we're actually looking at a limit of f of x minus f of a over x minus a as x approaches a, just in a situation where a happens to be the number 1, and our function is 7 to the square root of x. If that were the case, f of a would be 7 to the square root of 1, which is, of course, is just the 7. So instead of trying to power through this limit, I'm just going to switch over to shortcuts. This limit is a alternate form of the limit definition of derivative. So this limit is really just equal to f prime of x, or really it should say f prime of a. So if I've already recognized that the function is 7 to the root x, I can write that out. I can say f of x is 7 to the x to the 1/2, whose derivative, based on today, would be 7 to the x to the 1/2 times natural log of 7, and then chain rule. to give the derivative of x to the 1/2. But once I've written that out, I'm just plugging in a 1, being my a value, plugging in a 1 for x. And that is how I arrive at this final answer, which simplifies into 7/2 times natural log of 7. All right, if you have questions on the video, I should be back Friday. We're not doing too much on Friday. We can go through this stuff again as needed. There's a Delta Math assignment, and after that, there's a worksheet that we'll look at on Friday. So if you get through the video, those are the things you can work on. All right, if you have other questions, feel free to email me. Thanks for watching.